Hi everyone! I would like us to start some notes on Chapter 9 today. I will, as you can tell, not be here at school. I'm about ready to head to Missouri, so I just wanted to, I have a couple videos that you're going to watch after this one, but I want to introduce Chapter 9, and then we're going to, in the next two videos during your class period today, talk about the types of collisions, impulse momentum theorem, and then do some example problems of those collisions. If you do not get through all of the videos today as a class, then that's what your homework is going to be for tonight. So there's 3 links, all of them will be posted on your blog, so hopefully you'll make it all the way through this one, because this one will be pretty short, and then you should be able to get all the way through the next one, because it's about 20 minutes, and then the last one I think is about 15 minutes. So, whatever you don't get done, please just do it for homework tonight, and I hope to see you on Wednesday or tomorrow. Okay, so Chapter 9 is all about types of collisions as well as linear momentum. So when we talk about momentum, I want you to know that we're assuming or we are implying that it's linear. If it's any type of circular motion, then we will always designate it as angular momentum. So anytime you hear momentum, let's just always assume that they're talking about linear. Now we have focused so far all about Newton's laws, and we know that Newton's second law is just that force and acceleration have to be related. And acceleration we know is directly proportional to force, and acceleration is going to be inversely proportional to mass. But when force and acceleration vary with time, because a lot of times in our problems that we've done up to this point, then we've really just focused on that force staying constant, or if the force has varied, then we've taken integrals to find potential energy instead of really finding the force. So what happens if force and acceleration vary with time? Then it can get really, really complicated for us to use Newton's law, for us to use energy methods. So the technique that we're going to talk about in this chapter, Chapter 9, and dealing with momentum and collisions is really just another way for us to find a simpler way instead of having to make Newton's laws, kinematics, energy methods really, really messy. So we're going to develop a momentum version of an analysis model for us to kind of help deal with when force and acceleration are going to vary with time. One thing that I think really stands out in collisions is car crashes. I think it's like the best real-world example that we can just talk about to kind of get an understanding of momentum in the 2 different types of collisions that we'll focus on. So if I'm comparing the 2 cars here, I want to know what happens to these 2 cars when they collided. Well, in this example, there's actually damage to the cars. It kind of looks like right down here that the bumpers, whatever you're going to call that, I don't know, the front ends of the cars, it looks like, what it's looking like is that they're kind of stuck together. Now, 2 different types of collisions. One of the types is called elastic, and then the other type of collision is called an inelastic. So this shouldn't be new vocabulary for us because we did allude to this in AP Chem and in Honors Chem the last couple years, where that elastic collisions, if we go back and think about the kinetic molecular theory of gases, so elastic collisions are where 2 things can come in contact and they'll collide, but then they bounce right back off. So elastic is where we have the objects bounce off each other. So if elastic means that they're going to bounce off one another, then inelastic is going to mean that when they come in contact with each other and when they collide, that means that they're going to stick together. So elastic, they're going to bounce off, and then let's add that in the inelastic collision. And this pen is totally not calibrated, so I'm sorry. In an inelastic collision, what I want you to know is that they're going to stick together. So kind of like Matt and Rachel. So stick together and inelastic. Elastic is where they're going to bounce off one another. If we think about different things that happen in different types of car crashes, so each car, when it crashes, is going to experience a really large change in their velocity with a really small amount of time. So this car probably had to decelerate as quickly as possible so it wouldn't hit this car. So in that short amount of time, there has to be then a really large amount of force since there was such a sudden change in acceleration. So the amount of force that these two cars are feeling is one thing that we want to calculate, or one thing that maybe we want to manipulate when we're dealing with collisions. So the average force in collisions is typically very large. And again, that's only because we're experiencing a very large change in velocity in a very small time interval. So by Newton's third law, so let's just apply Newton's laws to these. By Newton's third law, each of the cars should experience the same magnitude of force. But by Newton's second law, the results of those forces on motion of the car is going to depend on the masses of each of the cars, and then also how much each one is accelerating as well. Now, how does this have to do with collisions and also energy methods? Now, in an inelastic collision, like we see this one here, because the bumpers here are stuck together, so this would be an inelastic collision because the two now become one giant system, because if I move one of them, I'm going to move the other one. So in an inelastic collision, when they have their own first initial velocities, but then in the final, after the collision, they have the same velocity. They're going to be moving together. That's different from an elastic collision. So let's say that this car comes up, maybe this car is at a stoplight, and then this car comes up, and then maybe very gently just taps on the bumper of this car, but they bounce back off. So that would be an elastic collision. An elastic collision also conserves kinetic energy and also conserves momentum, versus an inelastic collision, which will not conserve kinetic energy. I can tell that in this one because there's a lot of damage done to these cars. So I have to be losing energy just by deformation alone. I could have lost energy to sound. We could have lost energy to heat or friction. And that's what makes inelastic collisions a lot more serious and a lot more dangerous, because we're losing all of this extra energy just due to the crash itself. Okay, so before we get into the types of collisions, let's just define what linear momentum is, and then we can also talk about how that relates with Newton's second law. Because I keep telling you that when Newton works on his second law, everybody thinks that Newton did his second law because the apple fell on his head and he thought about how the apple was gravitationally attracted to the earth. But we know that's not true. He actually thought, how is the moon gravitationally attracted to the earth? And then how is an apple gravitationally attracted to the moon? Again, Newton doesn't really think in terms of forces. That was something that came later. His original ideas and his original theories all started with momentum. So it's an object's tendency to be in motion, or just an object's change in motion. So the linear momentum of a particle or of an object can be modeled as a particle of mass m. So let's just say can be modeled as a particle of mass, and we'll say that's m. So particle of mass m moving with a velocity that we'll just denote as v. So linear momentum is going to be the product of that mass and that velocity. We're going to represent linear momentum with the symbol p. So linear momentum is the product of mass and velocity. again, I already alluded to this, that the terms momentum and linear momentum are used interchangeably, so that's a really big thing that we know when we get to the angular momentum chapter, because if they just say momentum, they're meaning linear momentum, but if it has to deal with circular motion, they'll be very specific and say angular. Linear momentum, would you say that that would be a scalar or a vector quantity? Which one would it be? Okay, linear momentum is going to be a vector quantity. And the reason that it's going to be a vector quantity is because it's going to take the direction of velocity. So its direction is the same as the direction of velocity. We can, of course, express linear momentum in terms of all of its dimensions. So we can express it in terms of its component form. So maybe I'm talking about only the x direction, then we'll have the linear momentum in the x direction is going to be equal to m times v, but that v is going to be in the x direction. I can do the same thing for y. So the linear momentum in the y direction is equal to mass times the velocity in the y. I could do that same thing for the z direction. We'll get to the point probably either Wednesday or Thursday where we'll be doing collision problems but in 2 dimensions. And those aren't difficult, it just takes a lot of time because there's a lot of different directions that you have to account for. What are the units then going to be for linear momentum? So we said that linear momentum is, again, symbolized P, and that equals m times v. So if m has to be in kilograms, v we already know is a meter per second. So that means that the SI units for linear momentum are a kilogram meter per second. We don't have any special thing that we give that as a name for. It's not like a Newton, it's not a joule. So we're just going to have to call them kilogram meter per second. And again, Newton is the person that's really giving us this type of equation and is really helping us at the time understand that this is really the quantity of motion. Okay, so how does Newton's second law and linear momentum, how do they relate? In Newton's second law, we know that that's force is equal to mass times acceleration, or technically its acceleration is directly proportional to force and inversely proportional to mass. But we can use Newton's second law to relate the momentum of a particle based on a force that's acting on a given particle. So if I know that force is equal to mass times acceleration, to simplify that a little bit, because if we want to think about it in terms of momentum, then maybe I don't want to use acceleration so much, because momentum is really about mass and its change in velocity, and I could get acceleration because if I take the derivative of velocity, that gives me acceleration. So let me simplify that a little bit more. So let me say that force is really equal to mass times dv over dt, which is just the derivative of velocity, which is just acceleration. So those things are just going to be equal to each other. Now, if I manipulate this a little bit more, if I did what if I took the derivative of mv? Oh my goodness, I don't know why that just turned off. Sorry about that, guys. Because I think they do that because it's a Sunday and real people shouldn't actually be working right now. Okay, let's go back. So for force equals mass times acceleration, then all I did was sub in for acceleration, taking the derivative of velocity, because that means that it's going to give me acceleration, so those are equal to one another. But then, if I just kind of do a little bit of rearranging based on what we did just a second ago, and it should be coming back up at any minute, maybe This is really annoying. Oh, here we go. Okay, so let's say that instead, what if I wanted to take the derivative then of mv? Well then, really I'm talking about if I know that P is equal to mv, let me just substitute then P in here. So force should actually be equal to the derivative of linear momentum. So the time rate of change of the linear momentum of a particle is going to be equal to the net force acting on the particle. So the time rate of change of the linear momentum of a particle is equal to the net force that's acting on the particle. Okay, so if I just worked that in reverse, if I take the derivative of momentum, I know that momentum is mv. I'm going to take him out just because that's a constant. So if I take the derivative of v, I'm going to be left with m times a, which is equal to force. So that's how these, this and this can equal one another. So it's this type of logic or thinking that force is really just the derivative of momentum. This is the form in which Newton expressed his second law. So this is the form in which Newton expressed his second law. It is more general than the form that we have kind of used previously, but this type of form here, thinking about forces being the derivative of linear momentum, is going to allow for us that mass could possibly change, versus here, we always just assume that mass is constant. If we go back to that first car collision that we saw here, is the mass going to be the same of each one of these cars after the collision as it was before? Absolutely not. It can't be, because I would have lost some of that mass in the collision. Okay, so for us, we always want to talk about how momentum is conserved. So conservation of momentum can be expressed in a couple different ways here. If I think about the total amount of momentum in a system or in a collision, then let's just say that P total is going to equal the momentum of one of the objects plus the momentum of another object plus the momentum of another object, so on and so forth, just depending on how many objects that you have. So let's say that I want to talk about the total momentum in a car crash between two cars. Then that means car 1 has a specific amount of momentum, car 2 has momentum. So to talk about the total momentum of the entire system, assuming the system is two cars, then I need to think about the momentum of both of those cars individually. All of this then, total momentum, should remain constant. Okay, so what does that mean? That means that the change in the total momentum needs to be equal to 0. The change in the total momentum needs to be equal to 0. And actually, let me put a vector above momentum, because we are talking about a vector quantity here. So change in total momentum is going to be equal to 0. So that means that the initial momentum of both of the cars has to be equal to the final momentum of both of the cars. So if I said the initial of one plus the initial of another one, that has to equal the final momentum of the first car plus the final momentum of the second car. Okay, this will apply for us only when we're talking about isolated systems for momentum, which we're probably just going to focus on isolated systems for momentum. So we should have this just kind of in our wheelhouse where we say that total momentum should always be 0, so initial should always equal final. But they'll be consistent with you, and they'll tell you, let's assume this is an isolated system. So conservation of momentum can be applied to systems with tons of different amounts of particles. The momentum version of the isolated system model states, whenever 2 or more particles, in an isolated system interact, so whenever 2 or more particles in an isolated system interact, the total momentum should be constant. When we talk about the type of force that's being applied to a system, and we're focusing on that system's momentum, then in the conservation of momentum, there's really nothing that tells us the type of force that's acting on a particle. So it's not telling me if it's friction, it's not telling me if it's the normal force. I don't really care so much that it's the weight force. So identity of a force isn't necessary for us to continue on with our conservation of momentum work, okay? So we're not defining them or describing them as conservative or non-conservative, and it doesn't tell me really whether or not that force is going to be constant or whether the force could vary. So we can, when we're doing this conservation of momentum, we're always just going to assume that force could be varying. I don't need really big specifics about what's happening with the force, because all we're going to do is focus on what's happening to mass, what's happening to the velocity, and then also what's happening to the energy in this system. So let's do a very quick example, and then this is the last slide, guys, and we'll go to the next video, okay? So it says a 60-kilogram archer stands at rest on frictionless ice and fires a .030 kilogram arrow horizontally at 85 meters per second. With what velocity does the archer move across the ice after firing the arrow? So I know that, let's assume we are talking about an isolated system here. And if we're talking about an isolated system, then I have to follow conservation of momentum, meaning that the change in the total momentum has to be equal to 0, which means that the initial momentum has to equal the final momentum. I have 2 objects in this system. I have the archer, and I also have the bow. So initially it says that the archer stands at rest and then fires an arrow horizontally. So initially the archer is at rest and the bow is at rest. So initially here, that's just going to be equal to 0. Then let's talk about what happens to the momentum of both of them after he shoots the arrow. So afterward, I have the momentum of the archer. So let's call him M1. So M1 is going to equal the archer. So we'll call him M1, and then we know that he will also have a final velocity because it says that he's going to be moving across the ice somehow after that bow leaves after that arrow leaves. So M1, V1, we'll say that's final. Again, this is of the archer. Plus what I have going with the arrow, M2, and then V2, and then that's going to be of my arrow. Okay, we have the mass of the archer, he's 60 kilograms. For the mass of the arrow, that's 0.030 kilograms. I also know the speed of the arrow, which is horizontally, and let's actually, when we use this number, when we plug this in, we'll use this as, since it's horizontally, and they want to know what the velocity is. They're telling me that they want a direction associated with the magnitude of that velocity. So this would really be 85 roof meters per second, okay? I just want to rearrange this though and say, let me solve for this. So to do that, I'd have to subtract over here. So I would be left with, so M1 V1 final equals a negative M2 V2 final. I want to know what V1 final is, so let's just divide both sides by M1. Actually, I want to make that negative stand out a little bit more. There we go. Okay, let's just plug in our numbers. I would have 0.030 times 85 over 60 kilograms. All of that should be negative. So if I do that math, we should get the answer to be a negative 0.042 roof meters per second. And it should make sense, because if I'm supposed to conserve momentum, if one thing is, if I've applied a force and one thing is moving this way, then according to Newton's law, they're feeling the same amount of force but in opposite directions. So if the arrow's moving this way, that archer better be moving in the opposite way. And that's exactly what he's doing, because that speed or that velocity is negative. Okay, I'm going to stop here on this video. So somebody just get on your blog, open up the next video. You'll probably only have time then to finish up the second one, and that's okay. But whatever you don't finish, that is your homework tonight. And hopefully I will be back tomorrow. And when I am, then be ready if there may be an index card on your desk when you come in. Okay, bye.